Hi, everybody. This is Dr. Nigro with the Chemistry Notes screencast. This screencast is the next one in our series for our third unit, dealing with naming, balancing, stoichiometry. But this one is going to focus on empirical and molecular formula determination. So we're going to go through some definitions. All right, then we're going to practice an empirical formula problem, talk a little bit about what molecular formulas are, and then practice a molecular formula problem. Okay? So we're going to start out again with some definitions. The first is for empirical formula. All right, now I tend to abbreviate these as EF when I write them later. All right, but this is the simplest whole number ratio, also known as the subscripts, within your chemical formula. So of the elements within a molecule or a formula unit. All right. Now, one thing to keep in mind, ionic compounds are always listed as an empirical formula. We know that one of the rules for writing for writing formulas for ionic compounds is that the subscripts must be the simplest set. And what that means is they must be an empirical formula. So anytime you're dealing with an ionic compound, it should be in its empirical form. All right. Now, a molecular formula is a whole number multiple of the empirical formula that shows how the molecule exists in nature. All right. Never for ionic compounds. Sometimes for covalent compounds. All right. Now, because ionic compounds are built so that you get a neutral charge, that's why we get empirical formulas all the time. Covalent compounds are built differently. They are built based on sharing of electrons. And sometimes you need more of the elements to get all of the atoms within the molecule to have the correct number of valence electrons, the 8 that they want through sharing. So it's not as simple as what we see with our ionic compounds. All right. So the molecular formula of benzene is C6H6. What is its empirical formula? So we look at those subscripts and we ask if there's a common denominator, and here there is, 6. So if I divide both by 6, I get the simplest version of that formula, which is CH. All right. The molecular formula of octane is C8H18. What is its empirical formula? So I ask, is there something I can divide both of those by? And the answer is 2, right? I can divide 8 by 2, I can divide 18 by 2, and I get C4H9, and that would be the empirical formula for C8H18. So you can see that there's a difference between the empirical formula and the molecular, and it's an increase in those subscripts by some whole number factor. All right. So we're going to learn how to calculate the empirical formula first, and then we're going to work on calculating that molecular formula. All right. So there's a method that I like to run through when I do my empirical formula calculations, and that's when I'm going to teach it to you. And then I have this little jingle that I like to use, which we'll end with. All right. So the rules first. The first thing you need is to determine the grams of each element. All right. And that is usually given in the problem as grams, which is the easy way, or you're given a percentage. All right. So those are going to be your two choices, but you have to have grams of each element before you can really get going. Once you have grams, you need to convert that mass to moles using a mole conversion with molar mass. Whoops. So you need the molar mass of the element. And where would you find that, you say? Well, you're going to go look at that periodic table. That's where we're going to find that molar mass. All right, so now we've got moles of everything. All right, so you're going to look at those and you're going to determine which element has the least amount of moles and divide all moles by that value. All right. And what I mean by that is you're going to divide all of the mole values by the smallest. This is how we get whole numbers. This is how we get our subscripts for our formula. All right. Now, step 4, this is only if needed. All right. And this is not always needed. All right. But when you do that division by the smallest, if you get, whoops, let's do it this way. If you do not get whole numbers from step 4, nope, sorry, step 3, then you may need to multiply by a whole number. All right. So in other words, if you get 1.5 when you divide by the smallest, all right, we can't have 1.5 atoms. That's not allowed. We don't have half atoms, right? So I'm going to need to multiply 1.5 by some whole number to get that 1.5 to a whole number. All right. So in other words, if I multiply 1.5 by 2, then I get a 3 there, and I can have 3 atoms. That's okay. All right. But what you do to one element within the compound, you have to do to all of them. All right. So we'll do an example so you can see what that looks like. All right, now once we've done that, if needed, all right, then we use the whole numbers from step 3 or 4, if you had to do that, as the subscripts in the formula. All right. So those are the steps that we're going to go through, and we're going to be pretty systematic. We're going to do it every single time. All right. But my students know I like this little jingle. It's not really a jingle, but it kind of rhymes. So I kind of think it's a jingle. All right. But the way I say it is you start with percent to mass. All right. Then you go mass to moles. And then you're going to divide by the smallest. And then you're going to multiply until whole. Oops, until whole. All right. So just to look at this jingle, these two steps right here, the mass to moles divide by smallest, always, every single problem, you will do these two steps. All right. No matter what. All right. The other steps are sometimes. So this first step is going to be sometimes. If the problem gives you percentages, then you're going to have to convert percent to mass. And I do that by assuming 100 grams of my substance. All right. So what does that mean? All right. Well, let's say the problem tells you you have a compound that's 20% carbon. All right. If you know that you have 100 grams of that, 20% of 100 is 20 grams. So I basically just take my percent symbols and change it to a gram symbol. All right. So that's what I mean by percent to mass. Once we have mass of everything, it's mass to moles using molar mass. And then we divide by the smallest. And then if needed, we'll multiply until whole. All right. So percent to mass, mass to moles, divide by smallest, multiply until whole. All right. So we're going to do an example. Then I'll come back to this problem that's underneath. Oh, I thought we were going to do an example. Hold on. Let me see if it, sometimes they disappear. Oh, no, it's not here. Oh, none of them are here. All right. Well, I will tell you what the example is. All right. I had it on here, but it's missing. This is from our work packet. All right. And we're going to determine the empirical formula of a compound with 1.723 grams of carbon, not 0.289 grams of hydrogen, and 0.459 grams of oxygen. All right, so our job is to figure out what is the empirical formula based on this information. Okay, so as part of that, the jingle comes back. So percent to mass to moles, divide by smallest, and if needed, multiply until whole. All right, so we start with our first step, percent to mass. Well, we've already got mass, so we don't need this step. All right, so we're going to start right here at mass to moles. So we're going to take both of these, or all three of these, 7.23 grams of carbon. All right, a mole conversion, so that gram's going to go on the bottom and mole's going to go up top. And the molar mass of carbon is 1 mole is equal to 12.01 grams. All right, so I plug that into my calculator and I find that I have 0.1435 moles of carbon. All right, now I'm going to repeat this, but I'm going to start with hydrogen. So 0.289 grams of hydrogen, mole conversion. So the gram's going to go in the bottom. The mole's going to go up top, and 1 mole of hydrogen has a molar mass of 1.01. So we're going to get 0.2861 moles of hydrogen. All right, now, as I'm working through these, one thing to keep in mind, you do not round with these problems. If you round too much, let's say you say 0.3 there, when you divide by smallest, you are going to run into problems. So I tell my students to keep at least 4 numerical values. So that means I'm going out 4 decimal places for these. All right. In other words, the more decimals, the better, to be honest. All right. And then finally, oxygen, 4.59 grams of oxygen. All right. Again, the gram's going to go in the bottom. The mole will go up top, and 1 mole of oxygen has a mass of 16 grams. All right, and that's going to be equal to 0.02869 moles. All right, so I've done mass to moles. Up next, divide by smallest. So I look at these 3 numbers, and oxygen's moles is clearly the smallest. All right, so I'm going to start by dividing it by itself, which is going to give me a whole number of 1, and that will be the subscript for oxygen. All right, but then I'm going to repeat that for carbon, dividing it by the smallest, 0.02869, and I'm going to get 4.99, so that's 5. All right, then I'm going to divide hydrogen's value by this number, 2869, and I'm going to get 9.999, so that's 10. All right, so I have my whole number subscript. So I divide it by the smallest, and I do not need to multiply into whole because I have whole numbers. So my empirical formula is C5H10O. All right, now, generally speaking, for the order, all right, I tend to put carbon out front, hydrogen in the middle, and then anything else after that. At this point, just do the best you can. As long as you have the correct subscript with the right element, you're going to be fine. All right. So again, whenever you're working an empirical formula problem, remember the jingle: percent to mass, mass to moles, divide by smallest, multiply until whole. All right. So come back and you can see the screencast that deals with molecular formulas. We'll work another empirical formula as part of that. All right. But there's a couple extra steps that we have to do. All right.